Good morning. Today we will see how the light emitting diodes are made. And as we all know, in 2014, the Nobel Prize has been given for the development of light emitting diodes to Professor Akasaki, Professor Amano, and Professor Nakamura from Japan. And what is this importance of these light emitting diodes? You know, today when we talk about lighting, the lighting will come from the normal tungsten filament lamp, wherein the most of the energy is consumed for the development of heat rather than production of light. When you come to the tube light technology, which we see in our day-to-day home, in the tube light you basically have a tube, and within the tube you have a mercury. The tube is coated with a phosphor. When you have a mercury in the tube, when an electric field is applied, it will produce a discharge. The discharge will produce a light of wavelength 240 nanometer, and when this 240 nanometer wavelength light falls on a phosphor, the phosphor produces a white light. But the problem in these two technologies is, in the tungsten filament lamp, that is the incandescent lamp which was invented by the Thomas Alva Edison, the most of the energy is consumed for the generation of heat. Therefore, for the production of light only very minimum energy is used. That means, when you use for the electrical energy for the generation of the light, and worldwide nearly 50% of energy is consumed for lighting related applications. And if you could considerably reduce this usage of electrical energy by an appropriate technology, that itself will reduce the generation of electricity by conventional systems like using coal, using oil, because which contaminates the environment by polluting the environment, and then it will lead to green gas emission and will also have ozone depletion and all sorts of problems. Therefore, that is why the alternate energy efficient technology as the tube light. But in the problem with the tube light is, still it consumes more energy. Not only that, since it has a mercury in the tubes, when the tubes fuse off, we have to discard these tube lights on the earth. That means we basically contaminate the earth with a heavy metal like mercury. And when you contaminate the earth with the heavy metal like mercury, the mercury reaches the human beings or living creatures through water and other means. Once the human beings started consuming these heavy metals, then you know that it will entirely eradicate the human race or living race, because in the case of the human beings, it is very well known that the heavy metals will make the human beings impotent, and therefore it is environmentally not friendly when we talk about the tube lights. Therefore, the alternate technologies for the light emitting is these light emitting diodes. These light emitting diodes are basically a semiconductor based devices. Whenever we talk about semiconductor based devices, the consumption of electricity in terms of current is only in microamperes. In terms of voltage is only few volts. Therefore, by consuming few microampere of current, you could get light from a semiconductor device. And let us see how these semiconductor materials work to produce light. When you talk about semiconductor materials, we all know that one of the first semiconductor material in which the transistor was invented was germanium. But the germanium was not abundantly available on the surface of the earth. The people have moved to a silicon. Silicon is basically extracted from a silica, whereas the silica is abundantly available on the surface of the earth. Therefore, whenever we talk about any marketable product, the marketable product should be at an affordable cost. The cost depends on the resources. In the case of the silicon, since it can be obtained from silica, the cost of the silicon is low, and then it also equally do the job the way the germanium can do it. That's why the silicon technology has come forward. But when you talk about light emitting diodes, the light emitting diodes in which the electron and hole has to recombine and produce a light. But in the case of the silicon, the semiconductors are indirect band gap semiconductor. the recombination is happening by production of phonons. Therefore, when there is a production of phonon, the heat is generated, not the light is generated. Therefore, the other alternate semiconductor materials are compound semiconductors. The compound semiconductors are nothing but group 3,5 semiconductors, and group 3 we have a gallium, and group 5 we have arsenic, phosphorus, and similarly in group 3 we have indium. Therefore, by combining gallium, arsenic, you get a gallium arsenide. Similarly, if you combine a group 3 element indium and group 5 element phosphorus, you get a indium phosphide. We can also make an alloy of gallium arsenide and indium phosphide. We can make a quaternary, ternary and binary or pentanary systems also using these kind of combination like indium gallium arsenide, indium gallium arsenide phosphide. Such kind of combinations are possible. Therefore, in the case of the semiconductors, when you try to ally two different materials, and then you will get a linear properties of these semiconductors, because these semiconductor materials are all having or rather we can say that they obey the Vegard's law, and therefore the alloys can be formed, the lattice can be uniformly varied, and the band gap can be varied. Therefore, the wavelength which come out of these materials or the light which comes out of these materials can also be linearly varied. But when you look at the gallium arsenide and indium phosphide, the wavelengths are lies in the infrared region. If you make a p-n junction out of these semiconductors, and then wherein the electrons and holes recombine, the light is produced, because they are all called a direct band gap semiconductor. That means, normally what is an excitation? Excitation is basically we have to excite electrons from valence band to conduction band. When we excite electron from valence band to conduction band, and it leaves behind empty space which we call it as a positive charge holes, and then the electron goes to the conduction band. This excitation can be a two type. One is called an electrical excitation, the other one is called an optical excitation. In the electrical excitation, what you do, you will have a P and N as semiconductor, and in the P and N semiconductor, and when the P is connected to the positive and then N is connected to the negative of the battery, and which is known as a forward bias. When you have a forward bias, basically you excite an electrons, and then the electrons will recombine, and you can see that the light can come like this, or whichever way it has a path, the light will come out, and this is known as a forward bias. And that means basically this semiconductor device consumes in the current in the range of microamperes, and whereas voltages are usually 4 to 6 volts for a semiconductor device. But when you talk about an optical excitation, and which is normally used in the pumping of laser diodes, high power lasers, and when you have a laser which is incident on the semiconductor, if the energy of the incident light is higher than this band gap of the semiconductor, this is called a band gap of the semiconductor, which is normally represented as Eg, and if the incident light is higher than the band gap energy of the semiconductor, therefore then the incident light can again act as an excitation process, and then when you have an excitation process and you get a light out if it is a radiative recombination process. This is known as what is called an excitation process, which is very, very important. That is why today for a fiber optic communication, and we use the indium gallium arsenide phosphide, wherein we get the wavelength of 1.3 micron and 1.55 micron for optical fiber communication. Because when you use a silica fiber, the attenuation in the silica fiber is minimum when the wavelength is 1.3 and 1.55 micron. That is why we are using even today the indium gallium arsenide phosphide based the LED technology, or we can say that the laser technology, because when you pass 1.55 micron and 1.3 micron wavelength laser light through the silica fiber, the attenuation is minimum. That means the distance is very long. Therefore, you can transmit the light at a longer distance. Therefore, you cannot have a repetitor. And when you have more and more repetitor, the cost of transmission will be very high, and therefore it is very important that the attenuation is minimum, when you do the optical communication, that is in the infrared region. Therefore, in the case of the visible region, because when you talk about a visible light, we need to have light in the visible region. And the new materials which have been discovered is indium gallium nitride. It is basically an alloy of gallium nitride and indium nitride. The gallium nitride has a band gap of 3.4 electron volt, and indium nitride is a band gap of 0.7 electron volt, and another material called aluminum nitride is a band gap of 6.2 electron volt. What is the color of the light you expect? The color of the light you expect is depending on the content of indium nitride and content of gallium nitride and content of aluminum nitride in indium gallium nitride or aluminum gallium nitride, or you can also have indium gallium aluminum nitride. Okay? And then, for example, when you talk about aluminum nitride is 6.2 electron volt, and you know that using a famous Planck's equation, one can convert energy into wavelength using E is equal to h nu, and where E is the energy, h is a Planck's constant, mu is the frequency. Normally the mu is represented by c by lambda. That means basically which can be written as h is equal to c by lambda, or otherwise known as E is, the energy is inversely proportional to wavelength. Whenever the wavelength is shorter, the energy is very high. That's why when you talk about nuclear radiation, the wavelength is very, very short, but energy is very high. Then you get X-rays, then you get ultraviolet, then you go to visible light, then you go to infrared. Because when you talk about infrared, even our own body continuously emits infrared radiation. That is what used for recording infrared imaging process. And therefore, to make a green light, we have to mix indium nitride in gallium nitride with an appropriate composition. And if you could make an indium gallium nitride, wherein if an electron hole can recombine and produce a wavelength of 530 nanometer, then what you called, you get a green light. Okay? And today, whatever we see in the LED technology, which we use in the backlight of even our mobile phone, or the torch, LED torch, or in backlight in a TV, and the actual semiconductor chip will produce wavelength of about 410 nanometer. That means it produces only the blue light. When you have a 410 nanometer wavelength is incident on an yellow phosphor. When you look at carefully into the LED light, even in your mobile phone, you can see that a yellow coating is there. When you have an yellow coating, which is called as an yellow phosphor, when this 410 nanometer light is incident on this yellow phosphor, and you see that because of the excitations in the phosphor, you get a white light. Because whenever you want to talk about a white light, the white light is basically the primary colors. If you could mix red, blue, green, and you get a white light. And when you look at the sunlight, why it is white? Because when you look at the rainbow, you see the 7 different colors like Vibgyor, violet, indigo, blue, green, yellow, orange, and red. And if you could mix these rainbow colors, or if you could mix the primary colors like red, blue, green, you get a white light. And that is why what we see today as a white light from the light emitting technology. And in Crystal Growth Center, we have a facility to produce these materials. And also we have facilities to measure the given semiconductor is a P-type or N-type. Here in this center, we have a capability to have a 2-inch diameter wafer. On top of the 2-inch diameter wafer, which is basically a sapphire substrate, and we can make a layer after layer. For example, you can make an N gallium nitride on top of a P gallium nitride, or in other words, what we do in the laboratory, as you can see in the later part, and you have a substrate. On top of this substrate, you have a gallium nitride buffer layer, and above that you will have a N gallium nitride, and then you have a indium gallium nitride quantum well, and after that you will have a p gallium nitride. And then when you have these kind of stacking, and if the thickness of indium gallium nitride is comparable to the wavelength of electron, and if the thickness of the indium gallium nitride is higher than the wavelength of the electron, then you can see that there is a quantum confinement. And when you have a quantum confinement, basically what we do is we increase the density of states. That means whenever you in a semiconductor device, and if you have a quantum well like indium gallium nitride, and by using a forward bias, you will have the quantum confinement. That means basically the density of states will be increased, the recombination of electrons and holes will be very high, therefore the quantum efficiency of the device is very high. What do you mean by efficiency of your device? It has to consume less current and then produce a very good output in terms of light. That is what we talk about the efficiency. As long as if device consumes very low current, and then if the device can last for several years, that is the best from the customer point of view. That is also what we say about efficient light emitting diodes.